Okay, so what we're talking about today is graphing. Now, there's ways that you can do this with the graphing calculator. I'm actually not going to talk about how you can do all this stuff with the graphing calculator today. I want to talk to you about how to use Desmos. I think Desmos is a little bit faster. Let me rephrase. Desmos is way faster than your graphing calculator, but you can't use it on tests. So in terms of like, hey, I want to hurry up and get something done, it's great, but you need to know how to use your graphing calculator as well for a test. If you want to know how to do some of these things with your graphing calculator, you've seen all of it before. There are review videos by this guy, Rob, that I pulled off of YouTube and I posted on Schoology, so you can check those out. But to keep this video short, I'm doing this all on Desmos. So this first one, we need to find any intercepts algebraically and then use a graphing utility to verify. So graphing utility includes Desmos. So I'm going to show you how to do this on Desmos. It's real easy. You pull up desmos.com calculator. You can even log in if you want so that you can pull up your old graphs. All you got to do is just type it in. So it's, I've already forgotten. It is y equals 2x minus 5. Done. There we go. There's my graph. I can drag this around. It's really easy to get your nice window. And then if you want to know the intercepts, you can just click and then boom, there's my x-intercept at 2.5 and 0. And then here's my y-intercept at -5. Done. So I'm not going to actually do that one by hand. Next, we want to do this one algebraically and use a graphing calculator to verify my results. I am going to do this one algebraically. So in order to find the y-intercepts, you make your x value 0. We discussed last time that in terms of your y-intercept, if it's in that nice factored form, the number on the end, -2, is your y-intercept. So it is at 0, -2. Done. For your x-intercepts, you actually have to do the work of setting it equal to 0 and factoring and all that jazz. So 0 equals x squared plus x minus 2. So 0 equals x, let's see, we're going to do plus 2 and then minus 1. So our two intercepts, x-intercepts, are at -2, 0. And 1, 0. So if we wanted to check that using a graphing utility or Desmos, x squared plus x minus 2. Get rid of this one. To do the squared, you use a little caret. It's shift 6, 2, and then to get out of it, you just have to hit your arrow to the side, to the right, plus x minus 2. So now I can see all my intercepts. So there's the 1, there's the -2, here's my other -2 one, and it even tells us what the vertex is. Just automatically, it recognizes that it's a quadratic and has a nice vertex. Thank you, Desmos. You so fast. So other thing that we're going to talk about is testing for symmetry. So there's different ways you can test for symmetry. For the y-axis, if you want to find out that algebraically, other than looking at the graph, you plug in -x, so you do f of -x, and if that spits out the same function, it's symmetric to the y-axis. If you want to check if it's symmetric to the x, you slap a negative in front of your whole function and see if nothing changes. If nothing changes, it's symmetric to the x-axis. If you want to see if it's symmetric to the origin, you have to do both of those things separately and then see if there's the same. So you have to check x and y and see if they're the same thing.
Wait, oh, you want me to do two things? Man, I'd call my lawyer if dialing the phone wasn't such a hassle.
So this one I'm going to do on the PDF notes. So if you want an additional example of these ones, you can check out the PDF notes. I do this online. But we're going to do everything we were doing before on this problem. So once again, any x-intercepts or y-intercept is just going to be 0, as we talked about in the previous one. So y-int is going to be at 0, 0. So this one should go through the origin. In terms of my x-intercepts, I'm going to set 0 equals, and I'm just going to factor right away. So we've got x x squared minus 4. That's a difference of squares. So that's x plus 2 and x minus 2. And x 0 equals. So our x-intercepts are at the origin. Well, we knew that. It already went through there as a y-intercept. It's an x-intercept too. Should have another one at -2, 0, and we should have one at 2, 0. Let's just check all that in Desmos first before we do that symmetry stuff. Desmos. Get rid of this last one. So I need x cubed minus 4x, I believe it was. Let me double check. Y equals x cubed minus 4x. Done. All right, great. So there's our nice cubic. So we've got our intercepts there. We got our x and y intercept at the origin. And then we've got our other x-intercept there. Now we want to test this thing for symmetry. So first thing to do to check if it's symmetric to the y-axis, we have to do that. Can we go back, please? We're going to put a negative inside of our function, replace x with negative x, and see if nothing changes. If nothing changes, symmetric to the y-axis. So I'm going to replace that x with a negative x. And see if nothing changes. So if we cube negative 3 times, it's going to end up being negative, what is that? Negative x cubed. And then a negative x times a negative 4 is plus 4x. Okay. So now that that's simplified, that didn't turn back into this. So it's not symmetric to the y-axis. And you can even see that on Desmos. If you use the y-axis here as a mirror line, it doesn't look the same on both sides. So that's no good. Well, in terms of y-axis symmetry. Let's check x-axis symmetry. So for this one, we're going to slap a negative in front of the whole thing and see if nothing changes. So we're going to do y equals, and we're going to put a big old negative in front of everybody, like that. So we get y equals, well, we could distribute that negative in, and we get negative x cubed plus 4x. Again, it didn't turn back into this, so it's not symmetric to the x-axis, which you can see if you look at the graph. If we took this thing and flipped it over, there's nothing there. If we took this thing and flipped it over the x-axis, there's nothing there. So it's not symmetric to the x-axis. However, you might have noticed, going back to here, that this and that are the same. Since these two things are the same, it is symmetric to the origin. It's symmetric to the origin since both of those things are the same. So you can kind of follow points as they hop over both axes. This could hop over the y-axis and the x-axis, and it's found a new friend. If this thing kind of like hops over the x-axis and the y-axis, it finds a new friend. This one, same thing here. If it flips up and then over, it's got something to reflect onto. So this is symmetrical to the origin, but not the x or the y. All right. Whew, that was a lot. So we're gonna do that one more time on, I think especially with the amount of time that this is going, I think we're gonna do that. If you want an example of this, you can check out the PDF notes. I will do another example, but it'll be the same process. Yes, there's a squared there, but it's the same process. Yeah, same thing. Just keep doing that over and over. I do want to talk to you about even and odd functions. So this is just like a special property. If it's symmetric to the y-axis, it's also considered to be even. So it's symmetric to the y and it's an even function. If it's symmetric to the origin, it's also considered odd. So it's just an extra characteristic. It's symmetric to the y, which is a lot of words to say. So we just say, it's even. Or if it's symmetric to the origin, again, a lot of words, you can just say, it's odd. Mathematicians are lazy, and we want to try to find an easy way to talk about these things. So here's a bunch of graphs, and what we're going to do is we're going to kind of play around with these to say, what would it look like if, so here's part of it, what would this thing look like if it were an even function? Well, an even function means it's symmetric to the y-axis. Thanks to the wonders of technology, I can duplicate this thing, and what it's saying is it should be reflected over the y-axis, but it's got to be kind of mirrored. So I've got to oh, here. I can actually, there's a hyperlink thing for that. So I need this thing to be mirrored over the y-axis. So we get one that's kind of flipped to its partner, but it would kind of like continue there and kind of make a McDonald's thing. If it was odd, so let me duplicate this again. If it was odd, it would have to flip over the y-axis and the x-axis. So this thing would need to, once again, get mirrored over the y-axis, doing that, kind of making the McDonald's thing, but then it's got to be flipped again so that it's upside down, which was, I saw it. So I've also got to flip it over the x-axis, like this. So if I could have a little bit more space here, friend. So the even version is these two, but the odd version is this sort of upside down kind of loop-de-loo thing. You want to try to imagine those things connected together. You can do the same trick with these ones. So this one, we want to, if it's an even function, we just need to reflect this over the y-axis. Now, one thing that you'll notice is that certain points are not going to move. This point right here, once it's mirrored, is still going to be in that same spot. This point right here is going to get mirrored, but it's still in the same spot. It's on the axis that it's reflecting over. It's not going to move. It's going to stay in the same spot. So you could kind of connect these two with a little bit of line, and then boom, there you go. Same thing here. This is connected, and this is connected. So McDonald's thing, funny S, and then that thing, something like that. All right, we're going to duplicate this. We're going to do another one where it is on. So it's got to do a double flip. It's first got to flip over the y-axis, and you can do it in either order. It would get the same thing. And then this has got to get flipped over the x-axis. It's just got to make those two flips. Just like that. And now again, you're seeing some of this stuff is not quite moving. This point that's right at the origin is going to flip and flip, but it's got nowhere to go. This one flips over the y-axis, but then when it's flipping over the x, it's got nowhere to go, so it just stays right there. This line, however, since it was kind of floating out inside of the quadrants, it flops over there in this first change, and then it moves down to below. So there would be a nice open circle here, and this would be connected. I'm not going to do the last two. If you want to see additional examples of what the last two look like, go ahead and check out those online notes. Finally, what we're going to talk about is finding points of intersection when you want to see when things meet up. We talked about this at the very end of pre-calculus. Substitution works all the time, but can cause extraneous. Elimination method only works if you have matching degrees. So you can always substitute, but be on the lookout for extraneous, especially when the degrees don't match. Elimination will only work if your two equations have a matching degree that you're able to eliminate. So in this first example, they are matching degrees, so you can do substitution or elimination. Since they're both linear, you're not going to have extraneous solutions, but it's good to keep an eye out for. So you can do either one. This one is pretty boring. You've done these since you were in algebra, so it's not quite worth our time. This one I will do because it's a little bit more interesting. So we want to find the points of intersection and use a graphing utility to verify and make sure that we've got the right thing. And we'll even do that first. Sometimes it's nice to know what our answer is so we can kind of have that reassurance. So Desmos does a nice thing about finding those points of intersection. Here, I'm just going to do this because I can see what's going on. So I got x squared. So again, I did a shift 6 to get the little caret, to get that exponent, just like you would on a graphing calculator. X plus y equals 15, and then we got negative 3x plus y equals 11. There we go. Now I'm going to zoom this out a little bit so that I can see what's going on. Oop. There we go. So we've got 2 points of intersection. And Desmos is pretty smart. It knows that we're trying to find points of intersection. So if we click on it, we'll be able to see, hey, there's a point of intersection there. It tells us the actual coordinate. And then we get another point of intersection here at 114. So we got 114, and our other one should be, what was it? -4, -1. Should be our 2 points. But let's actually do that ourselves. Now these are mismatched. Since they're mismatched, I can use substitution or, if everything was mismatched, I'd have to use substitution. However, these two match, so I'm going to use elimination for this one. That way I don't have to worry about, extraneous solutions. So I am able to eliminate that y, so I'm going to use elimination. So I'm going to subtract these two equations. 15 minus 11, that's 4. The y's cancel out, and we get x squared plus 3x. And now that's a quadratic that I can set equal to 0. X squared plus 3x minus 4 equals 0. Do a quick factor. X plus 4 and x minus 1. Ooh, those are those numbers that we were getting before. So x equals -4 and x equals 1. Now we want to plug these into the lower degree equation, if I'm not mistaken. So you can plug into either one. Yeah, plug into either one. If you're doing substitution, you need to plug it into the lower degree equation. So I'm going to do the easier one, so I'm going to do the bottom one. So I'll plug in that x. So -3 plus y equals 11. So that's -4. So that's 12 plus y equals 11. Subtract 12, so y equals -1. So our first answer, -4, -1. Hey, cool. That's what we got on Desmos. And the other one, we got -3, -1 plus y equals 11. So that's +4, no, +3. And then we got to add it to both sides. Oh, wait, no, that's not -1, it's +1. That's an equal sign. So -3, add it to both sides, y equals 14. And that got us our other answer from Desmos, 114. All done. And I think that is about it for today. No, I think I'm going to do this one as well, because then we can see a substitution problem. So this one is ripe for substitution. Yes, you could kind of eliminate, but then there's these. So we're going to use substitution for this one. Since they both are equal to y, we can just replace this y with all this garbage and then solve that. So we get the square root of -x squared minus 4x equals the square root of x plus 6. Now you might be intimidated of all those square roots, but hey, you know, to get rid of a square root, you just square both sides. So we get -x squared, and that just gets rid of those square roots. Oh, how nice. Now we've got a quadratic, so let's get it equal to 0. So 0 equals x squared. Got to add a 4, so 5x plus 6. Do a quick factor. So let's see. We want to multiply to be 6 and add to be 5. So 2 and 3. So x equals -2 and x equals -3. Okay, so we want to plug this into the lower degree equation. So that's going to be this one. This one's got like squares and stuff in it. So let's plug it into that one. So y equals the square root plus 6. So if we do -2, we get y is the square root of 4. I don't know why I'm writing all this. So y equals 2. So our first answer should be at -2 and 2. And then in our second one, we get y equals the square root of -3 plus 6, which equals, let's see, that is the square root of 3. So we get our solution at what? -3 square root of 3. Okay, now remember this one has extraneous solutions possibly, so we have to check those out. We're actually going to use Desmos to verify that. So no, I don't want to use the graphing calculator. Again, Desmos is just so fast. So y equals, and we need a square root. So there's 2 ways you can get that. If this would get out of my way, can you get out of my way, please? Oh, well, there's 2 ways you can get it. You can do a 1/2, or there's supposed to be a little button down here. Oh, hide tools, there we go. And we can get a square root. So get a little keyboard. This is also, you can get pi and other things. So square root of x plus 6. Another one is y equals the square root of -x squared minus 4x. And we will take a look at our graph. All right, so we've got 2 solutions. So we got -3 and 0.732. That is our square root of 3 one, so that's good. And then the other one should be at -2 and 2. And that checks out. Now we can use Desmos to verify our solutions and make sure things are working correctly. Here, let me do, yeah, let's do it this. So we can type things into Desmos and make sure that it's calculating them for us correctly. So if we wanted to check like that -2 one, we could type in the square root of negative and then substitute in our -2. Squared. So all I'm doing is just doing that same thing, but not putting a y in front of it. -2, I missed the 4. And then boom, cool, it calculated it for us. Thanks, Desmos. And then you could really quickly swap in our other one, which was square root of 3. Oh wait, no, it was just 3. Or the answer was 3. The y value should be the square root of 3. Go away. Go. I don't want this anymore. There we go. Why isn't that one working? Is that one extraneous? -3. -3. My gosh. I am so sorry. There we go. And then we get our decimal answer again. Yeah. Cool. So I think that's about it for today. Thanks, everybody. It's not it for today. Anything else is going to be online. But here's our TLDR again. It was kind of in the slides, but you can do other things. If you ever are struggling with graphing and you don't have a graphing utility with you, you can always just make t-tables and just plug in numbers and see what you get. Keeping in mind like your basic idea of curves. So we're going to talk about that more next time when we start covering functions. Please remember these symmetry things. If you replace x with negative x and you get the same thing, it is an even function or reflecting over the y-axis. If you can slap a negative and nothing changes, it's reflective over the x-axis. If you can do both at the same time, you don't have to turn back into f of x. It becomes an odd function. Substitution always works, but gets extraneous. Elimination, you need to have matching degrees. So that's it. You want to move on to the check for understanding, so you can try out a couple of these problems. You can also go on to Schoology and see me work the worked out versions of all the problems that I skipped. So thanks. Bye-bye.